Okay, let's apply the strategy again to solve root 2x plus 1, then a minus 1 not in the radical, equals root x plus 4. Now, this follows the strategy because you do have a radical with a variable inside the radical. In fact, you have two of those kinds of radicals here. Just a quick comment though, the right side, sometimes people are tempted to turn that into root x then plus 2. You can't do that because that's trying to distribute a radical when you have a plus sign. And that'd be using the false formula of root a plus b equals root a plus root b. So you don't want to do that. Instead, we need to isolate a term that's a radical with a variable inside. There are two choices. Either the root 2x plus 1 should be on one side by itself, or root x plus 4 should be on one side by itself. But in the equation we're given, root x plus 4 is already on one side by itself. So let's just keep it that way and just square both sides. Okay, when you square both sides, on the right side, the squaring undoes the square root, so you'd be left with x plus 4. On the left side, we just wrote this as what was there originally, wrapped in parentheses, squared. Just another comment though, sometimes people want to try to distribute the square, but you can't do that. So this doesn't become 2x plus 1 then minus a 1 squared or anything of that sort. Okay, this is using a false formula. So we've talked about false formulas. You want to be careful to not accidentally use a false formula just because we're in the midst of doing something bigger. So instead, you'd have to FOIL the left side, and when you do that, you'll be left with 2x plus 1 minus 2 copies of root 2x plus 1, then plus 1, and the right side is still x plus 4. Now, if you add and subtract things on both sides, collect like terms, we still need to isolate a term that has a radical on one side. So I know there was a 2 in front of the radical, but the terms are separated by plus or minus signs. So the term that's on one side of the equation by itself is 2 times root 2x plus 1. And on the other side, you'll have x minus 2. And we're going to apply the strategy again, right? So we've isolated a term that has a radical with a variable inside it on one side of the equation. And now we should take that and square both sides. When you square both sides, on the left side, x minus 2 quantity squared. On the right side, the 2 times 2 is 4, and the radical times itself is just the contents inside without a radical sign. So 2x plus 1 in parentheses times a 4. The left side, just be careful again here. It doesn't become x squared minus 2 squared. That's using a false formula again. So you instead have to FOIL that out, distribute it out, expand, collect like terms. You'd have x squared minus 4x plus 4. On the right side, if you distribute 4, you'll have 8x plus 4. Let's get all terms on one side. X squared minus 12x equals 0. There's no constant term, which makes it really easy to factor, right? So you factor out an x. You have x times the quantity x minus 12 equals 0. Apply the zero product property. Add 12 to both sides of the second equation. So we end up with x equals 0 or x equals 12. Now the question becomes, which of these two numbers are actual solutions? Is it both of them? Well, we should go back to the original equation. Let's put that at the top of the next slide. So we started with the equation in the box at the top and ended with x equals 0 or x equals 12. So since we squared both sides at some point, in fact, we did that process twice, we're going to have to check to see if we have any false solutions. So is x equal 0 a solution? Well, plug into the left side. You end up with root 2, then minus a 1. On the right side, when you plug in x equals 0, you end up with root 4, which is a 2, and 2 is certainly not the same number as root 2 minus a 1. So because the left and right sides are not equal, x equals 0 is not a solution. This is an extraneous solution, or a false solution. Now, is x equal to 12 a solution? The left side, when you plug in 12 for every x, is going to simplify to a 4. On the right side, when you plug in 12 for every x, the right side is going to simplify to 4. Since the left and right side are both equal to 4, x equals 12 is a solution. So the conclusion here is that x equals 12 is the only solution. Please be careful here. Don't say that x equals 4 is a solution. That's sort of an error that I've seen occur. X equaling 12, so 12 is the value of x that makes both the left and right side simplify to the same number, and that number just happens to be 4. But that doesn't make 4 a solution. So it is okay to square both sides of an equation, but just be careful, because when doing so, you have to be sure to check for any false or extraneous solutions. In the last example we did, we saw that x equals 0 was an extraneous solution. So next time we're going to look at some other techniques for solving kind of other equations. So the whole point of this day and the next time is to look at equations that maybe are not as routine, but we have techniques to solve them. We just need to kind of talk through them. That's all. So next time we'll talk about substitution being used to create an easier looking equation, and we'll talk about equations with absolute value signs. So here are some practice problems that you could try that would use the methods that we've talked about here. Maybe look at, cube root of x squared minus 1 equals 2, or x to the 3 halves equals x to the 1 half, or look at 3 plus root 3x plus 1 equals x, or try x cubed plus 2x squared minus x minus 2 equals 0, or try root 2x minus 3 minus root x plus 7 plus 2 equals 0. For an interactive question, how about this? What would be a good first step based on the strategies we have discussed for solving x squared plus x cubed plus 2x squared minus x minus 2 equals 0?